plate tectonics. And then I'll have a number of lectures devoted to describing each of the type of plate tectonic plate boundaries in detail. So this is kind of a detailed lecture series intended for introduction to geology students who won't necessarily have access to live lectures. This is a USGS figure here, and it's showing all of the major different types of plate tectonic settings, just to give you an idea of what exists out there. And we're going to talk about each one of these boundaries in much greater detail in later lectures, but this is just an overview. You can see the convergent boundaries where two plates come together, they converge. You can either get a subduction zone, or if you have continent smashing into continent, nothing subducts. And these beautiful divergent boundaries where you had mid-ocean ridges, which we talked about in the last lecture. We'll talk about hotspots later. And those are kind of the major different boundaries. You also have these transform boundaries, which can accommodate for divergent plate boundaries, or you can have situations like the San Andreas Fault where you have side-to-side movement. And I consider these type of boundaries mainly accommodation boundaries or movement between the other two. And here is a layout of all the major plates in the world: the North American plate, the Pacific plate, and I think there might be some minor subdivisions of these larger plates, but these are the major ones, and I think they're appropriate for an introduction type audience. So what this lecture is intended to do is to add some additional detail on the evidence behind the theory of plate tectonics. And one of the most compelling and interesting bits of evidence is this idea of paleomagnetism. And there's some really interesting record in the rocks of our Earth's magnetic field over time. Something that not all of you might not know is that our magnetic field is changing over time, and it hasn't been consistent over the history of our planet. And sometimes it isn't even around for certain periods of time. It'll actually flip, and what is now our North Pole in terms of magnetism will flip and be the South Pole. And another thing worth noting is our magnetic north is not exactly aligned with the North Pole, the axis on which our Earth spins. And we can use the little atoms of iron molecules will align themselves with the magnetic field at the time. And these atoms are in igneous rock, right? And as that rock solidifies, it freezes those little compasses in the rock. And we can get an idea of what the magnetism was like at the time that rock solidified. And that allows us to interpret the ancient magnetism direction and magnitude in Earth's history. And here's a measured North and South poles over time, the North Pole being where all these lines come together, the South Pole being down here. You can see how that varies. You know, we've been measuring it since 1600s. Of course, we have it much further back in the rock record, but you can just kind of see how that moves around and wavers over time. This is a cool little GIF of that. And so here is what's going on at these divergent plate boundaries, where you have seafloor spreading. You're making new plate, and as you're making new plate, that magnetic field is varying over time, and you're basically creating like a magnetic stripe record of that magnetic field over time, and it's symmetrical across this plate boundary, right? It's this matches this on either side. Besides our interpretation of the magnetic record on these plates and how it's symmetrical, which supports this idea of generating new plate on either side of these ridges, we have the distribution of earthquakes and volcanoes, right? Here's earthquake locations over time, the major earthquakes from 1963 to 1998, and you can see that they align very well with our understanding of where the plate boundaries are. Sometimes there are exceptions, like hotspots and things like that, but for the most part, you get your densest concentration of earthquakes wherever you have interactions of tectonic plates. Same for volcanoes. The reason we have the ring of fire is because that designates the plate boundaries all around the Pacific Ocean, right? And a good chunk of the Pacific Ocean has these subduction zones where you're creating these large, explosive, and violent volcanoes, all the way from the Pacific Northwest, the Aleutian Islands, Japan, Sumatra, all of those areas have active volcanoes. And they exist in other places too, where we have subduction off the coast of, or along the western coast of South America, right? So they are lining up pretty well with those plate boundaries. Another kind of support and explanation from plate tectonics. There's also been a number of exploratory drilling vessels out there that investigated the magnetism of the oceanic plates, as well as sediment depth and age and things like that, finding older and deeper sediments as you move away from the ridges, which also supports that idea of seafloor spreading. And using the polarity of these plates and our understanding of paleomagnetism, we can get an idea of how old different plates are and how they get older as they move away from these mid-ocean ridges. So there's North America for reference, South America, and here's those mid-ocean ridges. And as you get to the cooler colors, that's older in terms of millions of years. And of course, we have GPS, and we've been measuring GPS motions, plate motions over time. And these arrows indicate a direction, and the length of the arrows indicate how quickly these plates are moving. So you can get an idea of direction and magnitude of movement over time. So GPS also supports our understanding of plate tectonics. And unlike Alfred Wegener, which we discussed in an earlier video of this series, we do have some hypotheses of a general understanding of what's driving these plate motions. A lot of time we attribute it to slab pull, which is the subducting slab, the slab that's going down into the earth. It's pulling down the rest of the slab with it, very much like a blanket hanging off the edge of your bed and sometimes pull the rest of the blanket off with it. And then this idea of ridge push. So the new, hot, young slab at the peak of that mid-ocean ridge is pushing down on the rest of the slab, and that's known as ridge push. And then we have convective flow, and it's still debated on how much the convection of the mantle is helping drive the movement of these plates, right? But you can see there's definitely been a lot of modeling done to see how these plates move over time. Here's India going into the Eurasian plate, creating the Himalayan mountains. And then here's plate motions over time, with seafloor spreading up to present, right? So you can kind of see how Pangea is breaking apart, creating the Atlantic Ocean basins, opening up that ocean. And then maybe if you model that movement forward into time, we can get another supercontinent. One idea that's been thrown around is the next continent being called Pangea Ultima. Not a very creative name in my opinion, but it's a cool concept nonetheless. And that is it for this series here. And we're going to move on to discuss the other ideas behind plate tectonics in the next videos. Thank you.